Okay, welcome to another operations research video. This one's on regression with a little bit of March Madness sprinkled in. Thinking of regression as an optimization problem. So in other contexts, we kind of let the optimization part of regression get swept under the hood. And usually we use kind of functions that will do the regression for us automatically. But in this one, we sort of are going to peel it back, do the regression or the optimization part of regression manually to kind of see what's going on there. Also get another example of um, quadratic programming, and then also more general nonlinear programming in a little bit. So we'll start off with a data set. So I've, for the last couple of years, been using March Madness as an example in a lot of my classes. So I've sort of scraped a data set of um, outcomes from March Madness games in the NCAA men's basketball tournament. And so this first line reads that data set in. It's made up of a bunch of variables and then a bunch of rows. Each row represents a game between two teams, and then for each team, we've got a lot of variables here, such as the seed of each team, the win percentage, and simple rating system, strength of schedule. For the purpose of this video, you don't need to know anything about basketball, but essentially these are just a lot of variables describing the team's performance during the regular season. Okay. And yeah, here, maybe I'll show you a little bit of that data set. So let's kind of pull that data set up. And so this first row of the data set represents Duke playing against Monmouth in the first round of the tournament. And Duke was a 1 seed and Monmouth was a 16 seed. And then all these variables with a .1 at the end are characteristics of Duke. And then all the variables with a .2 at the end are characteristics of Monmouth. Sort of their regular season win percentage at home, win percentage away, field goal percentage, 3-point field goal percentages. I'll let you kind of look at the key that I've provided here in the R Markdown file to, if you want to dig into what are those variables and kind of look at them in the context of what's going on with this regression. But the response variable that we're going to try to predict is the point difference in the March Madness game that the two teams played against each other. Okay, so one of the teams won, one of the teams lost. There was some difference in points, and we set it up so it's computed as team one minus team two. And so in this data set, I think I put the point difference way over here at the right. Team one, which was Duke, was the winner, and they won by 43 points. So it wasn't close at all in this first round first round game, which is often the case when you got a 1 seed playing against a 16 seed. They beat them by 43 points. Okay. But we're going to try to predict that point difference between teams with a regression model. Okay. Regression predicts quantitative outputs, and we've got a whole bunch of quantitative inputs that we'll put into our model. First thing we'll do is sort of clean up our data a little bit. Main thing is that we'll transform it and we'll extract the point difference and we'll call that y. All the other variables we'll put in x. And one other thing we'll do with that x that I'll kind of point out is that we'll look at all the variables as team one minus team two. So instead of looking at win percentage one and win percentage of team two as separate variables, we'll combine them into a single variable by just taking the win percentage of Duke minus the win percentage of Monmouth. And so if we go back here, Duke had a win percentage of about 90%. Monmouth had a win percentage of about 68%. And so in here, the win percentage difference is 22% difference between team one minus team two. Okay. And we'll do that for all the variables in the data set. And then I'll point out, we also added an extra column here of all ones, and I'll explain that in just a minute. Okay. So linear regression, we're essentially trying to build a model that predicts our output. And we're going to label that output y. That y is representing the point difference in the actual game that was played. And we put a hat on it to denote that this is a predicted value. And we're going to predict it by taking 1 times some constant. So these betas are going to be our coefficients that we're going to try to learn. The x's are our data. Okay, so they're the values in this X matrix. The I is sort of an index that goes down the rows of that matrix. So essentially it's indexing the games that were played. Okay. And then, so this xi1 would be first row of the data set. So first game played, variable 1, and then beta 1 would be the regression coefficient for that first variable. And beta 2 is the regression coefficient for the second variable. And so in here, the first variable is seed difference. And so beta 1 would represent the coefficient of seed difference, or the slope for seed difference. And beta 2 would represent the slope for win percentage difference, and so forth. I think there's 22 or so total variables here. Okay, and so we'll have 22 different betas that our model is going to estimate, as well as this beta 0, which is the intercept. Now, yeah, one thing I also did when I cleaned up the data, actually it's in the original data set, and how the data set is set up is I mirrored the data set so that each game that was actually played shows up in the data set twice, once with team 1 and team 2, and then another time with team 1 and team 2 swapped. And so there's one game in there where Duke is team 1 and Monmouth is team 2, and there's another game in the data set where Monmouth is team 1 and Duke is team 2. And then the point difference in that game is the negative of, or so the opposite of what it was in the first game. Okay, so don't worry too much about that, but that's sort of what it's set up as. And so I've got these I indexes that index the game, and I can think of this our prediction as being a vector, right? So as we go down that index, that's going to be a vector of predicted values. And we can represent this operation right here as a matrix vector multiplication, where we'll take our X matrix of our data and multiply it by a column vector of our coefficients. Okay, and so our predicted value is going to be our data matrix multiplied by our unknown coefficients. And we're going to let optimization help us decide what should those coefficients be. Okay. And they're going to play the role of decision variables in our optimization problem. For linear regression, which is sometimes called least squares regression, the objective function is we want to minimize the sum of the squared error. Okay, and so what we'll do is we'll take this y vector is the actual outcomes, okay, so the actual point differences, and then we'll subtract the predicted point differences. Okay, and the predicted point differences that I wrote as y hat over here is x times beta. Okay, and then we'll sum up over all of those the squared of each of those errors, or the sum of each of those errors. And this 1/2 out front just kind of helps the algebra work nicely. You don't have to have it there. It just kind of helps with the algebra a little bit. Now we can change this. Anytime you have a sum of squares, you can write it as a vector times itself, where you take that vector and write it as a row vector. So here I've transposed what I usually think of as a column vector into a row vector, and then multiply it by itself as a column vector. So whenever you take a row vector times a column vector, you're going to get a single number. Okay. And when you take the same row vector times itself as a column vector, you're going to get essentially the sum of the squares of all the entries in that vector. And so this is a trick that's used a ton in linear algebra and optimization. So this sum of squares is the same as that vector as a row vector multiplied by itself. And then I'm going to do some manipulation. And so some rule of thumbs when you're kind of manipulating matrix vector multiplications is that you can distribute, but you're not allowed to change the order of the multiplication, unless the quantity that you're looking at is a scalar, in which case you can kind of reverse the whole order of operations, okay, or transpose the whole thing. don't worry too much, but if you kind of distribute this out, you'll get a 1/2 y transpose y. So that would be the sum of the squares of all the original data minus y transpose, so these are the actual point differences, times x times our beta vector. That's going to be a number. And then we'll get 1/2 beta transpose x times beta. Okay, so this term here is going to be a quadratic term. This term here is going to be a linear term in terms of beta. Beta is our decision variables. This is going to be quadratic in our decision variables because you see sort of beta shows up twice, multiplying with itself. Here beta shows up once, so this is going to be a linear term. And then this term here doesn't have any betas in it, and so it's a constant, okay? And actually, in regards to our optimization, we can ignore it. It doesn't change the optimal solution, okay? It will change the optimal objective value, but we could just add that on after the fact. Okay, so this is our quadratic part, which we extract from here. So the x transpose x times 1/2, that's our quadratic part. And negative y transpose x, that's our linear part. Okay. And we can go ahead and build a model in ROI. Notice this has already got the 1/2. And so ROI, when you set up the Q matrix for your quadratic part of your objective, sort of assumes there is a half there. And so it's going to match up perfectly with what we've got. Okay. So here we're going to set up our regression model. We're going to set up a Q objective for a quadratic objective function. The quadratic part is T. So T of X is the transpose of X, which we write kind of mathematically as X with a little T in the X up top. So this is the transpose X. To do matrix multiplication in R, it's percent times percent. And then you're going to multiply that by the X matrix again. So our quadratic matrix is essentially this matrix transposed and times itself. Our linear part of our objective, we're going to take the -1, so there's sort of this negative out there, y transpose times x. And so that's the linear part of our objective. And then our names are the column names from this X matrix for our decision variables. The default bounds, and this tripped me up when I was first working on this and I was getting the wrong answers. The default bounds are 0 to infinity. And that worked well for our example where we were optimizing portfolios. But in this case, we might expect some of these slopes to be negative slopes, where that if we increase a variable, it's actually less likely that the first team wins, or that they're going to have a lower win margin of victory. Okay, and so we need to change the lower bounds to be negative infinity. And so we do that in bounds with this v bound for variable bound. And here we need to tell it which indexes we're changing for the lower bound. And so all of them, so 1 through the number of columns of x, which is the number of variables that we'll have. And then our lower bounds, we're going to have negative infinity, but we got to repeat that for the number of columns of x. Okay, and this one is a minimization problem, so we're going to set maximum equals false. So if we go ahead and run this and we look at applicable ROI solvers, we'll see that quadprog is an applicable solver because this is a quadratic program. Okay, so that's what we'll use as our solver, and we'll go ahead and solve it. It will give us an optimal solution. Here's the objective value. And then here are the coefficients for all the variables. Kind of get messed up in this output here. So let's actually write them to a results matrix, which I'll show you in just a second. But you can actually check that these coefficients are exactly the same coefficients as what you'd get if you did a linear regression with the LM function. And so, for example, the coefficient of C diff is 0.749. And then if I go here, the coefficient of C diff is 7.49 times 10 to the -1, which is 0.749. And so LM, which is your usual R function, if you ever want to do linear regression in R, don't don't use the ROI optimization package. Use LM because it's got sort of custom built machinery to do regression efficiently. Okay. Um, and so it's actually giving us the exact same thing as the LM function. Here we're going to just save those results in a results object, and then let's look at those results. And here maybe it's a little bit easier to see. I just named the method here least squares. We'll introduce a couple other methods in just a bit. And here are all the coefficients of all the variables or the slopes. You could think of them with respect to each variable. And so looking at it, it looks like, for example, if you take the win percentage and multiply it by 52, that's sort of part of the prediction. And so it looks like win percentage, keep in mind that's usually a pretty small number, has a positive impact on the point differential. And that if team one has a higher win percentage than team two, then they tend to win by more points in the game that they play against team two. Okay. Always be a little bit careful when you got multiple regression and you've got a whole bunch of variables. Especially in this case, a lot of these variables are correlated with each other. And so they're not independent of each other. And so some of the variables are sort of working together and kind of compensating for each other. And so you can get some things that seem counterintuitive when you've got a whole bunch of correlated variables. Okay. So let's go back in here. And I want to introduce a really powerful technique from machine learning, which is called shrinkage. Also, you'll hear it referred to as regularization. But this idea that we can improve the performance of our model if we introduce some bias. And so this is part of the bias variance trade-off. If we can often introduce some bias to reduce the variance of our models, and that will give us a better model in the end. And so this is not the video where I'm going to talk about the bias variance trade-off, but if you run into that in a machine learning class, this is connected with that, and that's maybe the reason why people might want to do this. But it's essentially the idea is that we want to, in general, we can get better performance sometimes if we shrink our coefficients, and that shrink them towards zero, and that yeah, that will give us better performance. And there's two ways that we can kind of shrink them, and both of them come via penalties that we can put on the size of the coefficients. And so the first penalty that we might be interested in is called ridge regression, where we penalize the what's called L2 norm, which is just a fancy way of saying the sum of the squares of the coefficients. And so in this case, we've got gamma, and that gamma controls how much we penalize it. But then that's being multiplied by the sum of the squares of those coefficients. And as I sort of mentioned before, anytime you got the sum of the squares of a vector, you can treat that sort of as that vector transposed multiplied by itself. Okay, and so this is one way to write the ridge regression penalty. LASSO is similar, but instead of penalizing the sum of the squares, it penalizes the sum of the absolute values. So it's a little bit of a different penalty. It has its sort of pros and cons, and I'll maybe point them out to you once we get to the results. But since we're kind of digging into optimization, we can kind of modify the objective functions to carry out these two penalty terms in that objective. So we'll have the same least squares objective plus one of these two penalties. And actually, there's a version called ElastiNet where you use both of these two penalties, and you can kind of put two different weights and kind of tune those two weights against each other to get the best possible performance. Okay. So let's start off with ridge regression. We're going to have the same objective that we had before, but then we're going to add, oops, I forgot to divide by the 2 there. But we're going to add this B transpose B or beta transpose beta there. And if you notice, we can kind of factor a beta transpose that's in front of everything out front. We can factor out a beta at the backside. you can think of there as being an identity matrix in between these two betas here. And so we can take these two terms and rewrite them as 1/2 beta transpose and then times x transpose x, but plus gamma times an identity function. And so what ridge regression does is it takes our x transpose x, the quadratic part of our optimization, and it adds gamma just along the main diagonal of that matrix. Okay. So that has some nice properties for linear algebra stuff, especially numeric linear algebra, where sometimes you can have an ill-conditioned matrix, and by adding something to the diagonal, it can make the numeric accuracy better. Okay. So yeah, so here's going to be our gamma. And so I set it to 100 to begin with. And let's modify this, our old objective, by adding this much to the quadratic part. And so here's what we had before. We have x transpose times x. But now what we're going to do is we're going to add on our gamma times diag is how you create a diagonal matrix, which includes making an identity matrix. And so I'm just making a diagonal matrix that is the right size. So it should be n by n, where n is the number of variables that we have, which corresponds to the number of columns of x. Our linear part of it stays the same as before, and our variable bounds stay the same. And so if we run this, here's the ridge regression coefficients that we'll get. Okay, which is good, but let's actually run it a bunch of times and see what happens as we change gamma. And so this is a for loop here. I provided a list of gamma values. And so I have 0 and then 1, and then I go up in multiples of 10. And so 10 to the first, 10 to the second, 10 to the third. So I go from 0, 1, 10, 100, all the way up to 1 times 10 to the 6, or 1,000,000. And this for loop essentially loops through from 1 to the length of this list that I provided. And what it does is it sets that ridge regression gamma to whatever the current value is in the list. Okay, and it loops through. And then we'll store it in the results object, and we'll take a look at it. So let's go ahead and run this. And then let's look at the updated results. And so here are the results. I've set the method to ridge. This column for hyper, that's going to be what holds the height, what we call hyperparameter gamma. And you can kind of see it's increasing here. And what you'll notice is that for each of the coefficients, as we increase gamma, these coefficients get shrunk towards 0. Okay. And it does it in a way that sort of balances the trade-off of wanting smaller coefficients while also wanting to do well at the least squares and minimizing the errors. And so it does it in a way that sort of balances minimizing error and minimizing the size of the coefficients. And as we increase gamma, we put more importance on minimizing the size of the coefficients. On the other hand, when we set gamma equals 0, well, we're just doing least squares regression. And so you'll notice the first two rows are identical to each other because they're solving the same optimization problem. Okay. So essentially, we've just modified the quadratic part, and we're kind of changing the gamma, and that shrinks the coefficients as we increase gamma. And that can lead to improved performance. These gammas are hyperparameters, which means that the ridge regression itself doesn't tell you what they should be, and you have to choose them outside the model. And the common way of choosing your value of gamma is to use what's called cross-validation, where you'll train the model or optimize the model on one part of your data and then measure its performance on a set-aside portion of your data. Okay, so that's ridge regression. Now let's turn to the lasso. Here we're penalizing the sum of the absolute values. Now, if you go looking on the internet, you'll find that there's a clever way that we could split our decision variables. our betas into a positive part minus a negative part, and then make b beta plus and beta minus both have kind of be variables from 0 to infinity. And then we could kind of implement an absolute value in a clever way there. And we could still keep it a quadratic program, but add some constraints. I played around with that. The linear algebra to get it set up was just messy enough that I didn't want to go there. And also, I wanted to show you a more general approach. Okay, so sometimes there's something that's more efficient computationally, but less efficient setup wise. And so here I'm going to show you something that's more efficient setup wise, though I will say it's less efficient computationally if you were to get a larger data set. So, but if you're just going to run it once, oftentimes the setup cost is not worth it. So what we're going to do is we're going to use a general nonlinear optimization strategy. And so in this one, we're setting our eta value, which is eta is the kind of the hyperparameter for LASSO, or at least the way I set it up. And we're going to set up, instead of pulling out the quadratic part and the linear part, we're going to set up just a function that computes the objective. And so we're going to take our y vector minus x times beta. So that's going to kind of compute our errors. We're going to square each of those errors and we're going to sum them up. And then we're going to add eta times the sum of the absolute values of the betas. Okay, so essentially this line here computes our objective value for a given beta. And so this is going to be a function of beta. And as we change beta, we're going to get different outputs. Okay, but we've sort of locked in the values of y, x, and eta. Okay, those are all sort of fixed as far as this function is concerned. Okay, whenever you create a function and are doing general nonlinear optimization, you usually get better performance if you also compute the gradient, which is the derivatives with respect to each of your decision variables. In this case, because we have this absolute values, and absolute values sort of end up in giving you sharp corners so that it's not smooth at that sharp corner, the gradient is discontinuous, or the derivative has a jump discontinuity in it. And so it actually performs worse in this case when you provide the gradient. Usually it performs better if you provide the gradient, assuming that that gradient is a nice continuous function. Okay, so this is what the gradient would be, but we're not going to use it. You'll notice that I've actually got it commented out down here. You can uncomment and experiment and maybe guess at why it's not performing well. But we're going to use ROI. Instead of using a Q objective, we're using an F objective. So this represents that we're providing our objective as just a general function, okay? And so we provide that function, and we name that function obj underscore lasso. We have to tell it how many variables we have. And then we have to, well, we don't have to, but we're going to give it the names of those variables so that it will give us our solution back with those same names. And here we're setting the same bounds that we're going to go from negative infinity to positive infinity. And it's going to be a minimization, so maximum equals false. Okay. Let's, here, let me run through some of this code and just run it just so that I can show you. Then if I look at applicable solvers, notice it's not going to say quadprog is an applicable solver anymore. It's because quadprog doesn't work on general function optimization when we just provided a function. Instead, it's going to suggest these two general solvers. Alabama, I tried it. It gave me a warning. Alabama is great if you have constraints. But if you don't have constraints, Alabama says, don't use Alabama because I'm built for using constraints. But instead, we'll use this NL, so nonlinear minimization. Okay. And so that's the solver that I'm going to use here. And here's the other important bit is when you do a nonlinear optimization with a general function, you're gonna need to give it a start value. Okay, essentially, you need to provide it an initial guess, and then it's gonna search from that initial guess and try to always move downhill towards that minimum. Okay, if you provided a gradient, it sort of knows which direction is downhill. If you don't provide it a gradient, what it will do is it will make a little search grid around the current point and then move in the direction or move towards the grid point that reduces its value. And if it doesn't find any reductions, then it sort of refines the grid and makes it smaller. And it kind of has a very clever ways of kind of expanding the grid and making it smaller to try to find that optimum solution as fast as possible. Okay. And so if you run this, you'll notice that the general nonlinear optimization takes much longer. Okay, it depends a little bit on the initial guess. In this case, the double function just creates a vector of zeros of the appropriate length. And so I started at 0, 0, 0, 0, 0. Okay, and it took a couple seconds to solve for this problem. And so then if we look at our lasso, it will say found an optimal solution. When I had the gradients turned on, it never found the optimal solution because I think it would sort of overshoot the solution each time. And then we can look at what those lasso solutions are, and here are those coefficients. Okay. Let's go ahead and kind of do the same thing we did with ridge regression and run it for many different values of eta and collect those into our results matrix. And so here again, I got a for loop, I got a list of eta values, and each time I set eta lasso to the current value in that eta list. And I'll store those then into the results. And I'll mention I did a kind of trick here in that the start value for the next value of eta is this previous solution, which should theoretically speed things up if we're giving it at least a decent guess of what the solution was with the last value of eta. But there we sort of ran it, I think 6 times was the length of that vector, 0 and then 5 other values. And it takes a little bit longer, much slower than when we just had a quadratic program. And so now let's look at the results. Here, these last 6 rows are lasso. And so here we're sort of increasing the value of the lasso coefficient. The interesting thing is that as you increase the lasso, a cool phenomenon happens where you'll have your value and then all of a sudden it will go to 0. And you'll have your value and all of a sudden it will go to 0. And so the lasso, using the absolute value of your coefficients as the penalty, has the tendency to drive some of your coefficients, some of your slopes all the way to 0. And as a result, it gives you what's called a sparser model, where your model is not even using all the variables. And that's kind of a nice feature where Lasso will automatically perform what's called feature selection and build you a model with fewer variables that then is simpler to discuss and talk about. And so you'll notice in the final model with the highest value of Lasso here, a lot of the variables are 0. But SRS difference, so the difference in this simple rating system, which turns out to be one of the strongest variables, is still non-zero. But I think if I scan over here, all the rest of the variables are, for all practical purposes, 0. And so this is in some ways saying that the simple rating system is the one most important variable. And back here, when I had a pretty high one, seed difference as well as simple rating system, I think were the only, as well as maybe opponents' points per game difference. So how much they gave up on defense was a little bit important, but all the rest of the variables are 0. Okay, so maybe this suggests that the overall simple rating system is a pretty good predictor. Seed has some effect. But then maybe the next most important one was how strong your defense is. And if your defense is giving up fewer points per game, then you tend to have a larger margin of victory in the March Madness games. Okay. So The goal of this video is just a neat application of optimization, another example of quadratic programming, but I also wanted to show you an example where you give just a general function of your decision variables to ROI, and then it's able to optimize that function. And if that function is convex, which in this case it was, when it finds a local minimum, it will be a global minimum. But in general, we're not guaranteed whether this solution would be just a local minimum, so locally the best, or actually the overall best. It turns out when you're adding things that are sort of least squares and absolute values, those are each convex, and their combination is also ends up being a convex function overall. But yeah, that wraps up this video of another example of optimization.